Arrays are a fundamental tool for developers, but their behavior can vary significantly depending on the programming language being used. In systems programming languages, it's necessary to specify both the type and size of elements the arrays will store. Scripting languages offer more flexibility, allowing for the addition of an unlimited number of elements while permitting the inclusion of diverse data types within the same array. So, are scripting languages just better? In today's video, we'll look at how scripting languages handle this issue, why it exists, and how lower-level programming languages overcome it. We'll also discuss why JavaScript arrays aren't even real arrays. Hi friends, my name is George, and this is CodeCrafters. Before starting, I want to send special thanks to the first members of this channel and to today's sponsor, CodeCrafters. More about them later in the video. Arrays are quite simple. They contain elements, each occupying a position. In programming, the first position is usually 0, the second is 1, and so forth. These positions are called indexes, which we use to retrieve and change the element at that position in the array. At a low level, the idea is to maintain each array element adjacent to one another in memory. But there's a problem here. Since memory also holds other values, arrays should not inherently expand. Disregarding this fact and adding elements could potentially overwrite other values that might be required later. In this example, immediately after adding elements to the array, a numeric addition operation follows. The problem here is that computers don't access values in terms of variables, but in terms of memory addresses. When the operation is executed, the machine code produced by the compiler instructs the CPU to add the numbers located in the specified memory addresses, which is right because it refers to where both values were initially stored. However, since both values were overwritten by the array, the CPU will execute the addition between incorrect values. As you can see, this presents a significant issue, one that is commonly addressed by simply not permitting programmers to add elements to arrays. This explains why arrays in systems programming languages lack methods such as append, insert, or push, as seen in Python, JavaScript, or other scripting languages, apart from the fact that arrays are not objects at low level. Let's see how systems programming languages enforce this basic rule. When the array is declared, we specify both the type of elements it will contain and its length, indicating how many of those specific elements the array will contain. The reason behind the inability to have different types within the same array lies in the use of this information to determine the required memory space for the array. The type specification informs the compiler about the number of bytes each element occupies in memory. By multiplying this value by the array's length, the precise amount of memory required to store the entire array can be determined. Whether the array is stored in the stack or the heap, this information is essential to know how much to move the stack pointer and allocating a sufficiently large memory space, respectively. You can check out my 2 previous videos for more details about this. Okay, here you see a clear distinction between elements. But remember, this is only an illustration. In the bare hardware, things look more like this, and the only information available to us is the memory address where the array begins, referred to as the base address. This is how indexing works. Since we know the number of bytes each element occupies within the array, when we want to access a specific element, we can calculate the memory address where that element starts. To achieve this, we add the product of the element's size and its position, referred to as the index, to the memory base address. This explains why we utilize 0 instead of 1 for the first element. When attempting to access the initial element, moving the pointer is unnecessary. As far as I know, the C programming language introduced this sugar syntax to simplify a process known as pointer arithmetic. And the reason why almost any major programming language out there uses indexing starting with 0 is because their syntax is inspired by C. Pointer arithmetic is a concept very important in C. I want to make a video about it in the future. But for now, here's a very good explanation about it from one of my favorite channels. To conclude this section of the video, it's important to note that the array itself does not contain information about its size. At this level of abstraction, an array is simply a block of memory, lacking an inherent property such as length, to verify the validity of an index being passed. Therefore, without caution, there's a high likelihood of attempting to access an element outside the actual bounds of the array. When this happens, there are 2 possible scenarios. If the array is allocated at or near the end of the memory granted to our process, the operating system will detect attempts to access memory locations beyond our allotted space. In such instances, the operating system terminates the execution of our process, resulting in a segmentation fault error. If the array is allocated further away from the memory limit, the operating system will not terminate the execution since we'll be accessing memory within our process's boundaries. In this example, even though we're accessing values out of the array, it doesn't matter if that region is holding other value, as everything is ones and zeros at low level. The accessed region will be interpreted as if it were of the same type as the elements within the array, allowing the program to continue execution. You might think the second situation is the best case scenario, because our program won't crash. But stop the video for a second and think about it. Is it preferable for our program to crash, or to continue execution under the assumption that the array actually had a fifth element? I mean, just imagine if this array represents purchases made by an individual. Okay, now that we understand why arrays can't grow and why they are limited to storing only one kind of element at a time, let's address the non-dynamic size behavior by utilizing data structures. But before that, a quick message from today's sponsor. If you follow this channel, you're probably the kind of person who loves to understand how things work. If you've ever wondered how your favorite developer tools like Git, Redis, or Docker work under the hood, the best way to gain that knowledge is by recreating them yourself. CodeCrafters offers challenge-based courses that guide you through crafting these tools step by step. If there is a concept that you don't know, their platform will provide you with the necessary information to help you continue progressing. The best part is you can start the courses by choosing a programming language of your choice. So you're not only recreating these tools, you're also improving your programming skills with the language you prefer. If you're interested and want to support me, you can sign up for CodeCrafters and choose the plan that best suits you using the referral link in the description below. I've been thinking about solving these challenges on stream, but I don't know if that's something you guys are interested in. I'm looking forward to hearing your thoughts in the comments. You can follow me on Twitter for updates on this matter. And now, back to the video. Data structures. In case you haven't watched my previous video, let me quickly explain linked lists to you. The simplest method to obtain a dynamically sized list of elements is by storing them wherever there is available memory space. To do this, we create a custom data type called a node. A node contains one item and one pointer. The item represents the element of the list, and the pointer directs to the address where the next node, containing the next element, resides in memory. We only need to maintain a reference to the first node, typically in the stack. When we wish to add a new element to the list, we search for an available space big enough for that node. Then, we update the last node of the list to point to the new node, which becomes the last one. This approach eliminates the concern about the list of elements growing. However, linked lists suffer from a significant drawback. They are not efficient for caching data. To give you some context, cache is a small, extremely fast memory embedded directly in the CPU. Its sole purpose is to store a copy of a small region of memory. When the CPU requires data, fetching it from memory can take a considerable amount of time, relative to the CPU speed, of course. But if the required value is cached, the process of loading data into registers can be orders of magnitude faster. When the data required for a CPU operation is found in cache, we refer to it as a cache hit. Conversely, if the data is not in cache, we refer to it as a cache miss. Due to its limited size, the cache cannot store a copy of the entire memory. For optimal performance, our data should ideally be as compact as possible, allowing it to fit into the cache and increasing the chances of cache hits. This may sound like a trivial concept, but when our programs are optimized to take advantage of caching, their performance can increase tremendously. Furthermore, in modern computing, cache isn't just a feature, it's the norm. Therefore, cache misses will be our primary concern for the remainder of this video. The problem? As linked lists elements are scattered throughout memory, they are very unlikely to be cached. Here, arrays are a clear winner, as they keep elements compacted in memory. But now we are back where we started. Arrays are too limited in functionalities. Here's where ArrayLists come into play. As the name suggests, we still use arrays, but in a smarter way. Instead of just holding a reference to an array, we create a data type that includes that reference. plus additional information about the array. When created, this data type allocates memory for an empty array. The capacity attribute indicates how many elements the array can hold, which in this example is 5. The length attribute indicates how many elements the array contains at any given time. Initially, since the array is allocated memory with no elements, its length is 0. The idea behind this data type is that it'll handle the array for us. So it comes with some associated methods. As the name suggests, the push method accepts a value and adds it to the array. Every time we add an element to the array, the length attribute increases. But note that eventually the array will be filled with elements. When this happens, if we try to add more elements, we'll exceed the array's bounds, which is exactly what we're trying to prevent by using this data structure. To prevent adding values beyond the array's capacity, we need to check whether the array is full before adding a new element. This is as simple as verifying if the length is equal to the capacity. If the array is not full, we can safely add the value of the new element. However, if the array is full, we need to allocate a larger array to accommodate more elements. Typically, we allocate a new array twice as long as the one that is full. During this process, we update both the capacity and the reference to the new array. This involves copying all the values from the previous array to the new one. Once the elements are copied to the new array, the previous array is no longer needed, so we free its memory. Finally, with free space available in the new array, we can add the new element and update the length accordingly. And that's it. Now we have a list of elements whose size can grow dynamically. And please don't tell me in the comments that this code can be written in better ways. It was written by my cousin, who knows more than you. Now, it's important to mention that this process of creating a new, larger array when the current one is full involves a heap allocation, which can have performance implications, as we discussed in a previous episode. Additionally, copying elements around in memory also incurs additional time. If you know the approximate or exact number of elements the array list will contain, and you're concerned about performance, it might be wise to create the array list with a specific initial capacity. This can reduce the need for frequent resizing operations, which means fewer allocations, which in turn means better performance. This is why in languages like Rust, you usually create a vector, the equivalent of an array list, using the new method, but there's also the with capacity method available. Another characteristic that array lists inherit from arrays is constant time access. Since elements are internally stored in an array, accessing an element at a specific position simply involves retrieving the element from the array by indexing it. This operation has a constant time complexity. To prevent accessing elements beyond the array boundaries, we perform a validation before indexing the array. This way, if the provided index is greater than or equal to the array length, we can return null, none, or a proper error. This effectively solves the problem of accessing out-of-bound elements causing undefined behaviors, which arrays by themselves cannot avoid. Though it adds an extra step, the time complexity remains constant. The reason I'm bringing this up is because in linked lists, accessing elements is not that easy. Unlike arrays, linked lists don't provide direct access to elements by index. As elements are scattered in memory, there is no formula to determine the addresses where elements reside. Accessing an element at a specific position in a linked list requires traversing the list from the head until reaching the node in the desired position. Since each node must be traversed individually, the time complexity for indexing, in quotes, a linked list is linear. The time complexity is not the only performance challenge here. Even if the desired element is in the cache, the other nodes along the path to find that element are often not cached, which can significantly slow down the traversing process. When is up to remove operations? After deleting an element from the array, all the subsequent elements must be shifted back one position in the array. So keep in mind that copying data in memory can be time-consuming. If the removed element is closer to the end of the array, the shifting process is faster since there are fewer elements to shift. If the removed element is closer to the beginning of the array, there are more elements that need to be shifted, which can significantly slow down the process. Of course, this also depends on the number of elements within the array list. Now, linked lists fanatics would argue that remove operations are faster, because everything we must do to remove an element is to update its previous node to point to the following node, and then free the unwanted node's memory. And yes, it is true. As no shifting operations are needed, the time complexity of this operation is constant. But we also should consider that, in order to update this node, we first need to find its value in memory. And as I've mentioned like 20,000 times, accessing an element in a linked list is not efficient due to caching. But before putting shame on linked lists, as we're going to do with JavaScript in a moment, consider that contrary to what it's usually said, linked list could still be a better choice in certain situations. And listen correctly, please. I said it could. Not all architectures base their efficiency on caches, nor in data shifting instructions. I'll read your comments about your opinions on this matter. At the end of the day, picking the right data structure depends on several factors. When you get into the low-level world, you'll usually find yourself benchmarking multiple solutions, attempting to wring out every drop of efficiency from the hardware. Now, before getting into the final part, you might have noticed that in both cases we created the data structure for a specific kind of element. Here, the array list can only hold 16-bit signed integers, while the linked list can only hold 8-bit unsigned integers. So, how can we solve this without having to create a different version for each type we desire? Well, if you are thinking about generic types, yes, you are right. But just to clarify, generics don't work the same way in all programming languages. In Rust, for example, when you declare a generic type, the compiler identifies each instance where you use that generic, generates source code specific to that type, and substitutes the generic type with the generated type. This process is invisible to us, as it's accomplished at compile time. As a result, in memory, we get data structured exactly as we expected. Another approach is employed by Java for custom types. If the type contained by the array is not primitive, instead of creating an array of values, the VM is actually creating an array of pointers, pointing to the memory addresses where the elements resides in memory. Here, the language is designed to hide all of those pointers from us, so we think we are dealing with arrays of values when in reality, we are not. If you are thinking this is bad for caching, yes, this is one of the reasons why Java is considered a pretty fast language but still slower than systems programming languages. With this approach, linked lists can get even worse, because nodes won't contain the actual element and the pointer to the next node, but a pointer to the element and a pointer to the next node. A cache nightmare. One that hilariously is very common to see in languages like C, where beginners are tempted to create something like this due to the lack of generics. And this leads us to the final part of this video. How do scripting languages handle arrays? Alright, let's quickly examine both the JavaScript and Python approaches. The first thing to remember is that scripting languages are typically not compiled into machine code. Instead, they rely on a special program to interpret the script, allowing it to mimic or emulate the desired behavior. Of course, to execute that emulation process, the real hardware is used. For this reason, such programs are often referred to as interpreters or virtual machines. When we declare an array, behind the scenes, the interpreter generates a specialized data structure to simulate an array of elements. To understand what Python does, we can explore the implementation of the official interpreter, which is open source. Here, we encounter a type called PyListObject. This is what the interpreter generates when we create a Python list. The documentation comment here states that this type is nothing but an array of object pointers. So it's similar to what Java does for non-primitive types, an array of memory addresses pointing to the values. But there's a key difference here. In Java, all pointers within the array point to values of the same type. In Python, these pointers point to objects, implying they can point to values of different types. This explains us being able to create an array and still being able to add multiple kind of elements to it. Because all of these pointers are of the same size, when we index a Python list, the interpreter simulates indexing the list by first indexing the array of pointers and then reading the value that the pointer is pointing to. And finally, let's talk about JavaScript. In simple terms, JavaScript arrays aren't actually arrays, they're hash maps. JavaScript doesn't concern itself much with arrays in memory. Instead, when a JavaScript array is declared, the engine creates a hash map where the keys correspond to the indexes. You can verify this yourself. Create a JavaScript file, declare an empty array, and then insert some elements at the position hello. As you'll observe, the indexing process is essentially syntax sugar for retrieving an element from the hash map by its key. Now, even though a lot of people claim that I don't like JavaScript, I have to admit that this is a very bizarre but clever solution. What's particularly fascinating about this is that if we add an element at position 1,000,000, the engine won't need to allocate memory for an array that large. Instead, it simply inserts another element into the table, accessible with the key 1,000,000. Very cool, huh? And that about wraps for now. If you notice that the animation quality decreases in the JavaScript part, it's not a coincidence. This video was particularly hard to animate, so hit the like button if you learned something. And if you want to learn more, consider subscribing and following me in other platforms. The subscriber count has doubled since the last video, so again, thanks a lot for your support.